Hi there, and thank you for clicking on this video. In this lesson, we are going to cover operations on functions. Please give this video a like if you find it helpful. Only takes a second to do that. Subscribe to the channel for more math help. Drop a comment or question to engage, and please check out the practice set for this lesson. Even if it seems like everything makes sense, it's so important to try it out on your own to make your own connections. So without further ado, what do we mean when we refer to operations? We use that word a lot in mathematics, and generally when I ask my own students, like, what are operations? It takes a beat for somebody to come up with something, and then they might tentatively offer an answer. So to clarify, in math, when we talk about operations, generally we mean like add, subtract, multiply, divide, and in this case, we're going to add something called composition, or to compose functions together. Now, there are other operations. So there are operations like take a square root or square it, or when you get into more advanced math, we might take a derivative or take a logarithm or something. But the basic operations, what we call like our four basic operations, are adding, subtracting, multiplying, and dividing. Okay, those are the main things that we do. And so when we're talking about operating on functions, what we mean is to add them, subtract them, multiply them, and divide them, and compose them. Now, composition is covered in its own lesson. So you'll notice we have some asterisks up there. Okay, I'm going to lead you down here. Composition is covered in its own lesson. So the other four operations, you already have a very solid foundation as to like what those operations are. We don't need to define what does it mean to add or what does it mean to subtract. But composition is going to need its own thing. So you're probably like what? All right, now that brings us to the notation, and I have like belabored this in my own classes probably more than I should. Now, you have to be given a function f and a function g. So if you remember from like your introduction to what functions are, we name them often with these letters. Okay, so we name them function f and function g. So you have to be given what they are. And then you'll see this notation over here. So looking here, this is f plus g, and then we have the of x. So the way we would read that out loud, we would say f plus g of x. Okay, it is not multiplication by x, okay? And that's even going to get more weird when we define what that means. That notation, f plus g of x, means to take f of x and add g of x to it. So it really looks like there's distribution going on. Like, oh, that's multiplication. We're just going to distribute the x through. I am aware that it looks like that. That is not what is happening here. So you have a function with the name f, a function with the name g. You're going to add those functions together, and the name of the new function is f plus g. Okay. Now, what I will often do with my own students is I will say, like, listen, if that is going to give you like some issues, you don't have to do the of x. You could just simply say f plus g, and what the variable is in that operation is kind of self-evident from whatever else is on the page. So it is okay to just say like f plus g. And in fact, I think I did that in the practice set video. So f plus g of x, that means to add them together. Here we have f minus g of x. So that would be our subtraction notation. And that means to take f of x and subtract function g from that. Now, this is our multiplication, and I am going to draw your attention to that. It is very important that you use a solid dot when you are multiplying here. So solid circle, f times g. What I refer to sometimes in my class is like students with bubbly handwriting. And you kind of know if your handwriting is bubbly. My handwriting is not bubbly. It's never really been bubbly. But sometimes people will say if they want to do 3 times, I get that good, times 5, they'll get a little bit bubbly and they'll be like, oh, 3 times 5. No, cannot do that. Okay, so No bubblies. Okay. So if you are multiplying, you must use a solid dot. And that is because the open, like open circle, is the symbol for that other operation, composition. Okay. And you'll see that a little bit further down. Here we have division. And you can see this as F over G like that. Okay, so you can see that like the tall way. Usually that's not an issue, but I have had students question like, what, like, wait a minute, is that different? Like, does the slash mean something different? No, it does not. And then here we have that open circle that I referred to. That is your symbol for composition. And so it is very important that you do those dots differently, that we know which one is multiplication and which one is composition, because we will do something different. And every year I make a big deal about that. I put it in like big letters, notes, like everything in the like, and every year when we get to a quiz on this material, students will get it wrong. They will not correctly identify which symbol that is. So kind of boring, yes, but also absolutely critical. All right, and you can see the asterisks there again, because composition, we're not going to address composition in this particular lesson. So we often practice on polynomials. That's because they are so straightforward. And a lot of times when you're studying this, you're either in a unit on polynomials or you have just rolled out of a unit on polynomials, but they can be performed on any functions. So we're going to start off looking at polynomials, and towards the end of the lesson, I'll throw in like a radical function, because at least in the sequence of these videos, if you are following along on my Algebra 2 playlist, you know that we have covered radical functions at this point. So here's our given functions. So we are given f of x is equal to 2x squared minus 9x plus 5, and g of x is equal to 2x minus 1. And so you have to be given those two functions, and then here are the problems that you would be asked to do, like add these together. And I will usually skip this, but that is the interpretation of that notation. So we're going to take function f and we're going to add function g to it. And this turns into pretty garden variety polynomial adding. So I've got the cosmetic parentheses around there. Cosmetic meaning it changes what it looks like, but it does not change anything that you're doing with this problem, just to set the two functions apart. And we just simply combine like terms. So again, I am way overkilling it on the number of steps that I am showing, but we would now combine them. So we've got the 2x squared. We've got negative 9x plus 2x, which is negative 7x. And then we have 5 minus 1, which is 4. And that is my end result. That is the function f plus g of x. F plus g of x is equal to, have parentheses around that, but I lost my dot. There it is. Okay, f plus g of x is equal to 2x squared minus 7x plus 4. And so there you go. Yeah. So next one is multiplication. So we have our big solid dot there. And so what that means is we're going to take function f, and there's our function f, and we're going to multiply function g. So because in this video series, I have really emphasized the area model for these operations, that is the one I'm going to use, but you are free to use whatever your teacher has told you to use. So here we have 4x to the third minus 18x squared plus 10x. Minus 2x squared plus 9x minus 5. And what I love about that method is that in general, your like terms end up on those diagonals. So we have 4x to the third minus 20x squared plus 19x minus 5. And of course, this is f times g of x. Okay, that is what we call our resulting function there. Okay, and none of that should be new. Okay, so if this is like absolutely brand new to you, you're like, what did she do? You want to go back and check out my videos on polynomials and like adding and subtracting and multiplying polynomials. So that would be in the polynomials playlist. Please pause this video, stop this video, go check that out. Okay, so you can follow along what we're doing there. Mostly, though, this is just interpretation of the notation so that when you see this new notation, you know what you are going to do with it. Now, with f divided by g, I often will not do this. So this will be literally f of x divided by g of x. And so we will have 2x squared minus 9x plus 5 divided by 2x minus 1. And in this case, I might leave that as is. I might tell my students, yeah, we're not going to get into the polynomial division, but it's not a bad thing to review polynomial division. So we'll take a look at this, but in general, like your teacher might be totally okay with you just setting it up. Now, the way I teach polynomial division on this channel is through that area model. In fact, the division is the reason that I am all in on the area model in the first place. Okay, it works for a lot of things. In our area, we look at the degree of the numerator, what we're going to divide by, which in this case is 2, and that helps us set up the number of columns. And then we have our divisor out here on the side. And essentially, this is like kind of like a factoring problem. Maybe not quite, but we have 2x squared, and we ask ourselves 2x times what would give me 2x squared? Well, that would be x, and then we multiply to get this lower left here. Now I have negative 1x squared, but what I'm trying to divide has a negative 9x in it, so these two must add up to negative 9, which makes this one a negative 8x. 2x times what would give me negative 8x? That would be negative 4. And negative 4 times negative 1 is positive 4. But if we look at our problem, we're not supposed to have a 4, we're supposed to have a 5, which means that we are short 1, and that 1 is the remainder. And so this would be x minus 4 plus 1, that is my remainder, over 2x minus 1. So I would often use this in my class as a review of polynomial division, because by this point, it's probably been a couple months since anybody's looked at polynomial division, and we don't want it to get too stale. So we come back and we take a look at it. But again, your teacher might have you do something different. Maybe you're doing this before you've covered polynomial division. Okay, so there we go. And I do want you to notice something here. Notice, again, because of the way polynomial division works, the denominator of the original expression is the same as the denominator on the fraction. If this divided evenly, we'd have a little bit something else going on that is more, it belongs more in a unit on rational functions, which may or may not exist at the time you're watching this video. So I have not done it yet, but you could be watching this video a year or two from now. Okay, so now I want you to notice something when subtracting. So for example 4, we've got f minus g and g minus f, okay, and we're working with these same functions here. So this would be take function f and subtract function g. This would be take function g and subtract function f. And with subtraction, the parentheses are not cosmetic. Okay, so I am going to be a little bit more careful. And this one would be 2x minus 1 minus 2x squared minus 9x plus 5. When we are subtracting, the most common mistake is to not distribute the subtracting to everything that is being subtracted. So we have here 2x squared minus 9x plus 5 minus 2x, and then this subtraction, of course, is going with the 2x, but it also goes with the negative 1. So you are subtracting something that's already being subtracted, which means it is addition. To subtract a negative means to add the opposite, so we're going to add positive 1. Over here, when I go to do that subtraction, we'll have minus 2x squared. Then we have minus the negative 9x, which will make it positive 9x, and then minus the positive 5. So it's minus 5, and now we just combine like terms. So on this one, we have 2x squared, negative 9x minus 2x, which is negative 11x, and then we have 5 plus 1, which is 6. Over here, our negative x squared, that's like kind of in the middle there, our x squared. Then we have 2x plus 9x, which is 11x. And now we have negative 1 minus 5, and that would be negative 6. And I want you to notice how these two answers are related. And it makes sense that they should be related because we are working with the same functions and we are performing the same operation. Which we have changed is the order that the operation is done in. So f minus g versus g minus f. And if you pause the video, I'll actually give you a moment. I'll stop talking for a moment and just give you a chance to look at those two answers. All right, I know moments of silence in the middle of a video are kind of awkward, but hopefully that gave you a chance to look at it. And what you might notice is that the signs are opposite. So we have a positive 2x squared versus a negative 2x squared, negative 11x versus positive 11x, and a positive 6 versus a negative 6. So they are actually the same terms, except all of the signs are flipped. So I want you to think about that. Think about, is that always the case? And if it is always the case, can you reason out why that is indeed the case? Okay, so kind of put that in the back of your mind. Now, a more interesting question when it comes to operations on functions is, what is the domain of the resulting function? Now, that is an interesting question to me. It might not be an interesting question to you, but like pretend that it is. So you've got these functions and you operate on them, and then you get this function when you're done. What is the domain of that resulting function? Well, the domain of the new function consists of those values that work for both of the original functions minus any excluded by the operation itself. So that's a little bit of mumbo jumbo-y, but basically your domain is all of your possible x values or all possible inputs. So we'll kind of review that definition there. So your domain is all possible inputs. So essentially, when you are, say, adding functions together, you're going to look at all the possible inputs for one and all the possible inputs for the other, and the ones that overlap. Okay, so they have to work for both. If you've got a value for x that works in one of them but doesn't work in the other one, it's not going to work in the resultant function either. Now, minus any that are excluded by the operation itself. Now, usually that's going to be division, but it can also be composition. Okay, which of course is covered in its own video. So today we're going to focus on the division. So any that are excluded by the operation itself, and specifically what we're going to pay attention to is the fact that we cannot divide by 0. So if you have division happening, you need to be mindful of the thing that you are dividing by. Now, when working with polynomials, this is often all real numbers. So if you are adding, subtracting, or multiplying with polynomials, the domain of a polynomial is all real numbers. Okay, that's like all your polynomials. Domain is all real numbers. If you add them, the domain is going to stay all real numbers. If you subtract them, still all real numbers. Multiply them, still all real numbers. Kind of boring. Now, where that's not going to be the case is with the division, because the division is going to introduce like what we call a restriction, because you can't divide by 0. Now, if you don't have polynomials, and we'll look at one that's like not a polynomial, we'll kind of explore what that is. But what I often tell my students is like, listen, if you are doing a high stakes test and you have to guess at this, all real numbers is just a good guess. Okay, it's just a good guess. It is not always the answer, and we will explore that, but kind of a valuable piece of information to keep in mind. So let's take a look at this one. Okay, so this is our problem from before, and we had f divided by g. So this would be f of x divided by g. And so that is 2x squared minus 9x plus 5 divided by 2x minus 1. Now, the domain of this first one, though, is all real numbers. That's a parabola. Okay, it's parabola, all real numbers. You can plug anything in that you want. This over here is a line, and the domain is all real numbers. So you would think, okay, well, if the domain of f is all real numbers, the domain of g is all real numbers, then the domain of like f plus g is all real numbers, which it is. But with division, you do have to be careful. You cannot divide by 0. Okay, so basically we cannot have a 0 here. Okay, so you can't have 2x squared minus 9x plus 5 divided by 0. Okay, okay, that is undefined. So here's where we go with this. 2x minus 1, whatever that is not allowed to be equal to 0. Okay, that denominator cannot be equal to 0. Now, this is one of these little things that I tend to do. We're just going to go ahead and solve this. So -1 plus 1 is 0. 0 plus 1 is 1. And then we'll divide this by 2. 2 divided by 2 is 1. And we end up with x cannot be equal to 1/2. If x is equal to 1/2, then we're going to have an issue with that denominator being equal to 0. So how would you write the domain of this resultant? There's different ways you can do it. So one way you could do it is to say all real numbers minus the set of 1/2. Okay, that is maybe like a good way to write it. So it's all real numbers except 1/2. 1/2 has now gotten excluded from this. You might see this. You might see just like x cannot be equal to 1/2. And that kind of implies that, like, yes, it's everything else. Like, just x cannot be equal to the 1/2. And so that's what we mean when we say, like, it's the values of x that belong in both functions minus the ones that are excluded by the operation itself. So let's take a look at one more thing here. Okay, one final example with domains. So we'll look at this one. So function f here. Now this is one that is not a polynomial. So I wanted to make sure not a polynomial, that we got one in here. Now what we know about these, okay, is that cannot be negative. Okay, because that's going to be an imaginary number. So if you try to take the square root of, say, -4, you'll end up with 2i. Okay, and we cannot graph that. Like, that is, we're just working in real numbers here. So we're not going to delve into our complex numbers. So what that means is that x minus 4, whatever that is, has to be greater than or equal to 0. It is okay to take the square root of 0. The square root of 0 is 0, okay? Because 0 squared is 0. But we do not want anything less than 0, so nothing negative. So greater than 0 is fine. Okay, we might get some yucky numbers in there, but like, they're real, and it can be equal to 0. And so what we'll do is we'll simply solve that by adding 4. And we get a domain of x is greater than or equal to 4. Now, this one is a polynomial. Okay, that is a quadratic. And so the domain of this one is all real numbers. So in this example, you can plug in anything you want for G. That's totally fine. But for F, we are restricted to things that are greater than or equal to 4. So I can do 4 minus 4 and get the 0, totally fine. I can do 5 minus 4, I can do 4.5 minus 4. So here's how this works. So this means f of x minus g of x. So f of x is the square root of x minus 4 minus x squared. Now that part seems like kind of boring to me. There's nothing you can do with that. You cannot combine those. Like, all you can do is just simply write them out. And this is why we do so many with polynomials, because that is boring. Now, this is where the question might get a little bit more interesting. What is the domain of that? So this is our resultant function. What is the domain? Well, the domain has to be the things that work for both. This one, everything works. So this is the one we need to be worried about. And what happens is that domain carries over into the new one. So in other words, this piece of it actually restricts the domain. Now, this can get more complicated. Like, what if you have a square root? Like, that also ends up in the denominator. And we'll check that out in the practice set a little bit. Are these kinds of questions super common? No, not super common. But you want to be able to reason your way through them, not just try to memorize stuff. So please check out the practice set. So if you found this video helpful, please take a moment to give it a like. Only takes a split second, just thumbs up. Subscribe for more math help. Drop me a comment or a question below. Let me know what you think. Let me know if it was helpful for you, or if you have further questions, or you think that I shortchanged something. Like, please engage, because I want to make my videos better. And check out the practice set. I will link that here, or any of the other videos on the channel. And I hope to see you in a future video.